It's great to be here. So today I'm dealing with two different pointers, so this is going to be really interesting. You guys are going to have a great time. It's going to be a bit of a show. All right, so I'm going to walk you through the gravitational wave spectrum. Steve did a great job introducing pulsar timing arrays and where we're sitting right now. I'll tell you a little bit about how pulsar timing arrays work and then walk you through why we're so excited about the gravitational wave background and where we're going next. So as Steve alluded to, I'll give you hints of signs of discreteness in the gravitational wave background. Something similar to what Roger mentioned, where if you find an excursion in the strain spectrum, what the heck does that mean and what do we do with that? Searching for continuous waves from the individual supermassive black hole binary systems and their host galaxies, and is there a hope in heck in finding them? And then the anisotropy that these induce in the gravitational wave background. So for the experts in the room, here's a spoiler alert. This used to be +5, but now everything's been shifted by about 5 years. So now we have evidence for the gravitational wave background. Continuous waves we hope will manifest in about 5 years. These induce anisotropy in the gravitational wave background, and then LISA will fly. Hopefully, this will all happen. All right. So as Steve said, Chris Moore came up with this beautiful GW plotter code back in 2015, which we were all very, very grateful for. And at the very high frequency end of the gravitational wave spectrum, you can see that LIGO sits up here, where you could potentially hear the black holes merging. They make the characteristic whoop sound as they're merging. LISA is in the millihertz frequencies, and pulsar timing is at very low frequencies. And we're most sensitive to a stochastic background. So this is like a low frequency hum, kind of like the om at the end of your yoga class, right? Where everyone hums together and makes that great sound. And so these are all complementary gravitational wave detectors. The experts in the room will object and remember Alberto Susana's famous paper, which links LISA and LIGO, but that's not the purview of this talk. So the strain that we're sensitive to with pulsar timing arrays is around 10 to the minus 15. And that is, the strongest sources of gravitational waves in the whole universe. These are the most massive supermassive black holes. And we use millisecond pulsars to detect them because we're looking for this fractional change in time over time that's of the order of 10 to the minus 15. Something that Steve likes to say, that now I like to say too, which I think is great, is that in terms of a change in distance over distance, this is the size of a virus over the diameter of the planet, right? That's crazy. So we have huge variances in scale with pulsar timing array detectors. Our supermassive black holes are gargantuan. There are 1 billion solar masses or more. We time them, and we time the gravitational waves that are emitted by them by using pulsars that are 1.4 times the mass of the sun, right? They are so massive. They're so massive and so small, it's like putting something that's the size of the sun in a blender and then timing it. It's crazy. The physics of that are crazy. And importantly, I want to emphasize that our supermassive black holes are not transient in our band, right? These are very low frequency, slowly evolving sources. And so one of these supermassive black hole binaries can spend tens of millions of years in the pulsar timing array band, which is great news because we've never found them. And so this experiment basically gives us training wheels for LISA, where things are going to be zooming around, merging within a week or so. So we are at the IOA, and I want to point out that Martin Rees published one of the first papers on limits from pulsars for this cosmic gravitational wave background. And what's really interesting in this paper, first of all, he published it with my academic great-grandfather, Bruno Bertati, and Bernard Carr, who's still doing great work. And this paper is really interesting because it was submitted before Hellings and Downs submitted their paper and before the discovery of millisecond pulsars. So actually, at the end of this paper is a really wonderful addendum saying that they were dismissive of the prospects of correlating noise in the pulsars because the pulsars were just too noisy. And at the very end, it says, this was added after the paper was accepted. There's this discovery of millisecond pulsars, and these might be stable enough to look for gravitational waves. So it was really a beautiful paper and very prophetic. And my second link to IOA was from when I was in high school and emailed Martin Rees because that was something you could do back then in the early days of the internet, when I got one email every 2 weeks from my Hotmail account. I was doing a project on terraforming Mars and was very concerned about what Phobos and Deimos would do to the colonizers on Mars. If the tidal forces from all of this water that we would manifest on the surface of Mars would flood them. And then he kindly replied 2 weeks later, which was instant back then, saying that tidal forces go like 1 over the distance cubed, and these aren't very massive objects at all, so you really don't have to worry about it. So I was relieved. I was very relieved for our future on Mars. Finally, this figure here that I'm showing in this realization comes from a paper that I wrote with my dad in 2018. And this was over a disagreement that we had at Christmas dinner over a little bit too much wine. He's a mathematician, and I said that I integrated something numerically. He said that he could, that this was a straightforward application of the Riemann-Lebesgue lemma, and then we wrote a paper showing that he was right. So the millisecond pulsars that we're timing, their residuals look like this, and the residuals are the expected minus the actual arrival times. So the whiter these residuals look, the better. Any kind of long-term structure in here that you can see by eye might be a bad thing. It could be that those pulsars have red noise in them, and we expect that red noise to be a gravitational wave signal. So if the pulsar intrinsically has red noise in it, it's really difficult to tell that apart from the gravitational wave background. So we don't want to see that. So this pulsar here, 1713, is one of our best pulsars, but also it's also so bad that it has its own Instagram meme channel about everything that breaks with this pulsar. The way that we find the gravitational wave signals is from cross-correlating all of these residuals. The gravitational wave background signal should be the only signal that's correlated between all of the pulsars in this pulsar timing array. And so when we cross-correlate pulsar A and pulsar B, 2 things pop out. One is this characteristic strain, which is the sum of all of the strains from all of the gravitational wave emitters at a particular frequency, and this angular correlation function, which is the Hellings and Downs curve. And so we believe that there's a stochastic gravitational wave background that is likely sourced from supermassive black hole binary systems. And so what creates the stochastic background is likely the incoherent superposition of hundreds of thousands to millions of simultaneously in-spiraling supermassive black holes. And what's great is that this is the most boring explanation we have of the gravitational wave background. Other sources could be primordial gravitational waves, from processes like ekpyrosis, where you have these, recycled universes that are expanding and contracting that have blue tensor indices. Importantly, all of these signals create the Hellings and Downs curve. So when we see the Hellings and Downs curve, we know there exist these gravitational waves, but we don't know what sources them. And so figuring out what sources these gravitational waves is really important now. So the Hellings and Downs curve, as Steve showed us in his talk, is this interesting quadrupolar-like function. It starts at a half here, but it actually goes up to 1. It's normalized to 1. If you were being very careful, you would see these little Bessel function oscillations that quickly dampen here that get you to the Earth term only solution. This part here at pi is half of what you have at 0, and you can just prove that using easy geometric arguments. And so there's been a lot of discussion in the community of do single sources also make Hellings and Downs curves, right? And I was curious to know and completely unconvinced by any argument that I'd heard. So I got a good undergraduate to actually make me the Hellings and Downs curve source by source. So here on the sky, you have 1 point, that's one source. And then here you have the real Hellings and Downs curve. And then this is the curve that's created from this point on the sky. So you can see this looks nothing like a Hellings and Downs curve. But then as you go, and you add about 15 sources, then you get something to 1 sigma that's very Hellings and Downsy. I'm going to trademark that. And as soon as you get to 500 sources, then you have something that's within 0.05 sigma of the Hellings and Downs curve. Now, the Hellings and Downs curve is a really interesting correlation function. It implicitly assumes that your gravitational wave background is isotropic. But clearly, I just showed you proof that it's not. Right? You build it up source by source, so how on earth could that really be isotropic? It can't be. It also assumes that your gravitational wave background is sourced by plus and cross polarizations and completely ignores any kind of Einsteinian contributions to that. And this can change for alternative theories of gravity and different propagation speeds also of gravity. So Steve just showed us this beautiful figure that the NANOGrav collaboration, Steve was one of the lead authors of this paper together with Sarah Vigeland. We took 15 years to make this measurement. Each one of these points, even though their error bars are large, was hard fought, right? 15 years of going back to telescopes every 2 weeks to take another time of arrival, another timestamp, going back, writing grants. It was a huge effort to create this measurement. So the prediction is the Hellings and Downs curve. The measurement has the big error bars, and then this is no gravitational wave background. And so even though this looks like it's not a lot of points, these are actually 2,211 binned pulsar pairs. And there were 21 new pulsars that got us from the 12.5-year data set to the 15-year data set. So earlier there was a question about what would you do? Would you, wait, or would you get more pulsars? Well, you always want more pulsars because your SNR depends on the number of pulsars and only on the square root of time. So you always want to add more pulsars. But of course, Steve said he would never reject a pulsar, which is good for him. So 67 pulsars have timelines that are greater than 3 years, and those are the ones that we used. And we get Bayes factors of 900 to 1, which are pretty good odds that there is a gravitational wave background manifesting in the data. And so what can we do with this information? Well, the first thing that I'm curious to do is to try to constrain the underlying astrophysics of the supermassive black hole mergers. And you will be very clearly convinced that I think that the gravitational wave background is sourced by supermassive black holes. So what can we learn from this? Well, here we have this beautiful looking double integral. We basically just need to focus on two things, that it's a function of chirp mass and it's a function of galaxy merger rates. And so when we measure the amplitude of the background, and now we have a pretty good measurement of this amplitude, we can in turn constrain things like galaxy merger rates and black hole masses as a function of redshift. For the cosmologists in the room, you can relate this to omega GW. It's proportional to the characteristic strain squared. And again, I want to remind you how the characteristic strain comes out. It's from cross-correlating all of your pulsar residuals. So you cross-correlate your pulsar residuals, you get the Hellings and Downs curve, and then you also get an amplitude of that. That's how you get all of these terms. So f to the minus 2/3 is a really nice, straightforward analytical prediction, but doesn't necessarily give us reality, because in reality we have discrete sources. We don't have an infinite number of sources we can average over at each frequency. So my student, Andrew Casey Clyde, made this really nice rainbow plot where here you show the number of binaries as a function of gravitational wave frequency. And we found that at around 26 nanohertz, you really get a strong deviation from the f to the minus 2/3 power law. And we see that there's a knee there. We're not the first people to point out the fact that the background can break down here. Alberto Susanna pointed this out in 2008 as well. He's done so many things, it's amazing. So this is good news and bad news. The bad news is the background is gone. The good news is the background is gone. And so at these high frequencies, you can now start searching for the individual supermassive black hole binaries without having to worry about the gravitational wave background interfering with your signal. And so I told you that when you have a measurement of the amplitude of the background, you can decompose it into these underlying physical parameters that govern supermassive black holes and their mergers. And indeed, that's what we did. And so here we have a limit on the number density of sources, which is 1.1 times 10 to the minus 5 per megaparsec cubed. The minimum mass of black holes contributing to the background, which is about 10 to the 8 solar masses. And also that the gravitational wave background should be enclosed in a volume that goes out to redshift of about 2. Oh no, I was doing so well. Okay. And so then what's next, right? So now we have a handle on black hole masses, the volume of the background, that's cool. But what else can we do? So again, we know f to the minus 2/3 is a good starting place. But what happens to the strain spectrum when you go to much lower frequencies or wider binary separations? Your gravitational wave strength is very low there. You're not really driving your binaries to merge through gravitational wave emission. Here, gas and stars are doing a much better job at moving your binaries closer together than gravitational waves are. And that results in the gravitational wave signal being depleted. The residence time at those low frequencies becomes much shorter than it otherwise would be if it's gravitational waves. And so that makes our strain spectrum turn over. So this could be caused by eccentricity in the system. Now you're not emitting gravitational waves only at the fundamental harmonic, but now you're emitting them at all of these other higher order modes as your binaries are circling each other. And you can also have scattering that happens. Say that you are someone that's claimed for many years that supermassive black holes stall. Well, that's fine, because you'll eventually have a third galaxy that comes in with its own supermassive black hole that scatters off your stalled binary and takes away the lowest mass one, and your eventual two remaining binaries can merge. And so isn't it interesting that we have this really interesting turnover-like feature in the strain spectrum that we measured, right? So this is the cartoon of what we think this will look like. This is exaggerated and cartoony just to guide your eye. But in the data, this is what we find. So this is the measured strain spectrum with the NANOGrav 15-year data. This paper was led by Luke Kelly. And you can see here, this is your straightforward f to the minus 2/3 model. And this is the best fit model. So that's interesting. It's not yet convincing, right? This is a base factor of a few that prefers this turnover, but we're not really sure. We also saw something else happening, right? So these are just two different ways of representing the same data. What is this, right? If this is what we expect, what on earth is happening at 16 nanohertz? So I told my student that he needed to figure this out because this is driving me crazy. And so at 16 nanohertz, we call it the 16 nanohertz excursion. We created 1,000 realizations of realistic supermassive black hole binaries, and then plotted the 15-year residual spectrum, which is blue, and then thought, well, if this is something like a single binary that's at that frequency that's pumping more power into that frequency bin, surely this must have been visible in the 12.5-year data. And so Steve's student, William Lamb, went and reprocessed the 15-year data to put it into the 12.5-year bins so that we could plot them all together and do an apples-to-apples comparison. And this is the only bin that doesn't change between the two data sets, right? Some of them look messy at high frequencies. You expect that. You don't have a lot of sensitivity there. But here you have a 2 sigma-like excursion from your expected f to the minus 2/3 power law. So one interpretation of this is that it's just noise and it's nothing. But the optimist might say, aha, this could be the first evidence for a continuous wave, some additional gravitational wave power at that frequency. And so here's a few candidates and how they would be within 2 sigma of the allowed parameter space of such a binary. What's also interesting, and again gets back to Roger's question, was what if you have significant deviations from the f to the minus 2/3 power law? Well, you actually expect that, right? We have a discrete population of supermassive black hole binary systems. And you only, on average, over thousands of realizations, expect to get this kind of power law behavior. But in our one realization of the universe, we're going to have lots of crazy stuff happening. And in fact, it didn't take long to find one realization from Andrew's runs that showed, we can actually get a 16 nanohertz excursion very easily. And in fact, we can have many of them. And all it takes is one more binary than you would expect at that frequency to create that kind of spike in the strain spectrum. So it's not at all unexpected that we should see that. The next thing that we want to try to figure out are where are the supermassive black hole binary systems? And so there's been simulations that show that there are these periodic light curves that can trace individual binaries. And there's been a lot of work done trying to track these down. There was the CRTS catalog, for example, that was put together. And a lot of work that's been done by NANOGrav. What I want to highlight is that if we know the sky location of a source and we know its potential frequency from these periodic light curves, we should be able to do up to an order of magnitude better in the chirp mass upper limit for that binary. And so Mitch showed us these 2 really interesting PKS sources. And I jumped out of my seat because we've been very excited about those sources. And so my students did a search for gravitational waves in those galaxies and found base factors of 1, so we don't expect there to be supermassive black holes there convincingly, but we do get new constraints on the binary masses that are about 15 times 10 to the 9 solar masses for PKS2131, and then something like 23 times 10 to the 9 solar masses for J0805. So Mitch is right, we don't really have the sensitivity to make a detection of these yet, but now we're looking at them, we have a pipeline set up for it, and with IPTA DR3, when we combine all of our data, we really think we'll be able to place much better limits, or maybe even detect some of these. So we have a big team that's working on following up 13 of the AGN in the CRTS sample, and our results are currently in preparation. So Steve showed this great animation, and I'm so happy I get to show it to you again, because one of the things I'm really excited about is finding anisotropy in the gravitational wave background. This is, of course, induced by discreteness, unless you believe in anisotropic inflation. And in fact, one of my first papers was on anisotropic inflation. So maybe, right, that could be fun. But if it's not that, and if it's supermassive black holes, we'll eventually be able to bring the gravitational wave background into focus and see these underlying sources. So I've been thinking about this for a really long time, and so is Steve. In fact, Steve led the first search for anisotropy back in 2015. Andrew Jaffe's even joined the party, which has been really fun. Other cosmologists are now really interested in this as well. And so just to give you a sense of what this looks like, if you have this, a realization of discrete supermassive black holes, and you want to say, what does the gravitational wave background look like? If you have a strong source, you get this one pixel that's lit up, right? And when you do the angular power spectrum of this, this one pixel really dominates everything. If you subtract that, you get a CMB style map underneath, and you can look at its angular power spectrum. Over many different ways of doing this, I've found that really anisotropy is about 20% of the monopole. And finally, in order for us to do a lot of this work, we need better pulsar distances. And so there was this Gaia fever at CCA, and Vasily was there, and lots of people were there, and we had these Gaia parties, and I thought, I can't be the only schmuck that doesn't do anything with the Gaia data, right? I can't let this happen, so like, what can I do with Gaia data? And so I thought, well, you know, millisecond pulsars have binary companions, and the pulsars aren't bright and optical, but maybe their companions are. So what if I use Gaia to look for their companions, and they're in sufficiently tight binary systems that that's basically like pointing at the pulsar itself. And in fact, that worked. So this is the latest figure. This is an example of a pulsar, J1012, that had a VLBI measurement. And we found its companion in Gaia DR2 and in Gaia DR3. And when you combine your peaks, when you combine the posteriors, because these are all independent measurements of the same quantity, so you can, you know, normalize the posteriors on the distances and multiply them together and then do much better. And so in fact, moving from Gaia DR2 to DR3, we found a 30% improvement in the measurements, and I'm looking forward to the next Gaia data release. So this will enable future tests of general relativity. It'll help improve detection prospects for continuous waves. And importantly, it'll enable the detection of these supermassive black hole dynamics over thousands of years of evolution, which is something I'm very, very keen on. And there's also been studies done that show that this improves our fuzzy dark matter bounds. Okay, so to summarize, we've just observed the first evidence for the gravitational wave background. And it's not just NANOGrav. All of our colleagues all over the world now have different levels of evidence for this gravitational wave background, which is really exciting. So our local nanohertz sources, we hope to find them in a few years. And instead of doing all sky searches, what my team is working on is really doing targeted searches, trying to figure out what's the probability of any one of these galaxies hosting a binary. But all of the approaches at this point are really important. Anisotropy, maybe, it's a work in progress. Right now, I have a paper in preparation with a really talented student in Padua who's doing cross-correlation between large-scale structure and the gravitational wave background. And what we found is that there are different kinds of anisotropies. So Steve alluded to this a little bit earlier, and Bruce Allen is now really interested in this as well, where you can do, when you can look at the anisotropy as a function of frequency. And at very low frequencies, the anisotropy does in fact follow the large-scale structure because there's lots of sources there. And at high frequencies, it's what cosmologists would call shot noise. And what we would call just the individual binaries, right? So it's kind of like a Poisson noise all over the sky. So there's anisotropy everywhere. It just depends on what frequency you're searching at. So what's next is really everything. So thank you all very much for your attention.